Hi MTV, my name is Nate DeBonville, and this is my maid audition. I was born and raised in San Francisco, and I always dreamed of being an ice skater. All the cool people knew how to perform triple axels, but me, I'd always fall and mess up and never understood the concepts. Please, MTV, help me obtain my childhood dream of becoming a male figure skater. Who's that? Who's at the door? Who are you?
Hi, my name is Armando Gonzalez. I'm a world-class figure skater.
Nice to meet you.
And now I'm your main coach.
You gonna help me?
Yeah, first of all, sit down.
Oh, damn.
These next 6 weeks are going to be long, hard, tedious work. Are you up for it?
I think I could try.
No, I don't want that. I want yes or no.
Yes, definitely. It's been my dream.
Come on, let's go.
You sure you're gonna help me?
Get up, come on.
Come on.
Nate, get up. You're late for your first practice.
What time is it?
It's 6 in the morning. Come on, get up.
Oh, hey, I'm sorry, Armando. I must have overslept.
That's all right. Well, for our first lesson today, we're going to learn how to spin. But for the sake of time, you got to learn how to spin in a chair before you get on the ice.
Sure it's gonna be sturdy?
Good? That's good. Just get on it. Okay, whenever you're ready, just give it a nudge. Just spin. Okay, now bring them in.
Ooh.
You notice you went faster when you went to close your arms?
Yeah, why was I going so much faster with my arms closer to me?
I'm not really sure, but for that, I have some friends that could help us out.
You gonna go call them?
I'm gonna go call them right now.
Alright. Hey, how you guys doing? Come on in.
Thanks.
Armando told me he called you guys.
Yeah, we heard you had a physics question for us.
Yeah, he's trying to teach me how to be a male ice skater. You know, we were practicing spinning on the stool. He said we started like this. Then I brought my arms closer. And as I brought my arms closer to my body, I was spinning a lot faster, and we don't know how that works.
Well, it's because when your arms were close into you, you were conserving your inertia, which means you're conserving your kinetic energy. And also you're conserving your angular momentum, which means you're going faster.
Alright, see, I'm trying to be a figure skater here. You guys are obviously physicists, so English translation, please. I don't know.
Alright, let's break it down. First, we need a couple of things. We need the radius of your arm length open like this, and then the radius of your arm length closed. And then we need how many revolutions you do in seconds, and also your weight in kilograms. So how much do you weigh?
180 pounds.
Okay, we can convert that.
All right, and I have a handy dandy tape measure. So arms open, and we'll get that. On the center. So about 92 centimeters exactly in close your arms. All right. And that is about 26 centimeters. All right. And the last step, we need to time you.
Alright.
Yeah.
Does anybody, you guys have a stopwatch handy?
Oh, yeah.
Alright.
So arms out.
Alright.
Hold on, 1 second.
Got it working?
Ready?
Alright, let's go. Bring it in. Man, it's gonna be hard on ice.
That was about 2 seconds.
Alright.
That's 2.
Alright.
Now we go to the drawing board and figure this out.
Alright. Let's go.
All right, Nate, come take a seat. We're going to teach you some physics and explain why you're going faster. All right, well, we're going to use the conservation of angular momentum. Here's the equation, which I know looks a little complicated. But what it means, this is the initial inertia and the initial omega, which is pretty much here before when you had your arms out. And then, which equals the final inertia and the omega final. And this is what we need to find, because this determines how fast you're really going when your arms are closed. So I set up the two problems. And we need to find the initial inertia, and then we need to find the final inertia first. And the reason why I have these two different equations, Melissa will explain why.
Okay, well, there's different equations to find inertia for various objects, such as, I got this book, and this is how I got the equations. So first, we used this one, and then his arm length out acts like a rod going through the center of his body, and so we calculated that through for his initial, and then for final, his body was acting like a solid cylinder, and so we used 1/2 mr squared, and that's how we found his final.
All right, now since we have all the numbers, so 112, and the mass is the mass of Nate. So since you said you're 180 pounds, we converted that into kilograms. And then this, the length right here is when you had your arms open, which was 92 centimeters, convert to meters, so it's 0.92 meters. Solve for that, and your initial inertia was 5.77 kilograms times meters squared. And then for your final inertia, we use this equation. And so once again, 180 pounds converted into kilograms. And then this length is different because this is when your body was, when your arms were tight. So it was only 0.26 meters. So after you solve all that, your final inertia was 5.53 kilograms times meter per second squared.
So now we're going to find, still going on trying to find omega final. First we need omega initial. The formula for that is 2 pi times 1 revolution per over the time for 1 revolution. Plug that in, 2 seconds. The initial omega is pi times rads per second. Now we've got all the information and we can finally plug it into the formula. All the numbers, initial inertia, initial omega, final inertia, and this is what we're looking for. Do all the calculations, the math. We got the final angular velocity has 1.04 times pi rads per second, and we can convert that into 0.52 revolutions per second. So when your arms are closed and you're spinning at 0.52 revolutions per second. Which is
Wow.
pretty fast.
That's pretty,
Yeah.
All right.
man, maybe I should go find my maid coach.
All right.
Hopefully explain it to him.
All right.
Hey, so you understood all those concepts I was telling you about earlier, right?
You understood it, Nick?
You got it?
Well, there's one more aspect to the conservation of inertia problem. Actually, it's kinetic energy.
You got another part to this problem?
Yeah.
Oh, but I do understand kinetic energy. And since this is the initial, this is when I first had my arms open, when I started the rotation, did one of them. And we know the initial inertia and the initial omega. We plug in the numbers and we get the initial kinetic energy equals 28.38 joules.
Oh, and since this is the final kinetic energy is when you have your arms closed. So this is the inertia for this, and the omega for that is 5.53 and 1.04, and it comes out to 28.47, which is almost identical to the initial kinetic energy, which should make sense. So, do you understand it, Nate?
Yeah, I get it. Now I just gotta put this, put it into action, go out on the ice skating.
Yeah.
Yeah.
Because you have a competition in about 30 seconds.
30 seconds? Why didn't you tell me earlier?
Kind of nervous, but I think he's gonna do okay because my boy prepared him right, and he should be doing fine.
Guys, he's on TV right now.
Armando, I got 18th place out of 20.
That's great.
Man, I did not get last.
Woo, go!
Yes.
Yeah, that's all we can wish for.
You
I
saw
did
you
with
saw
that.
me doing this, right? Woo.
Yeah.
And then I brought it in, and man, I got it. I got
Good,
it. You
good,
made
good.
me. You made me. It's all you.
It's good.
Thank you. Appreciate it. Hi, this is Nate again, and I was just made into a male figure skater, and I want you to know the people that helped this all come true.
I'm Armando, and I was a maid coach.
My name's Stephanie Miller, and I was the physicist.
I'm Melissa, and I was a physicist.
And I'm Christina, and I too was a physicist.
And we are the
Bums.
Bums.